Hi guys, today we're going to continue lecturing in Chapter 7. Before spring break, we got through the first page and a half of our Chapter 7 notes. We talked about Lewis dot for individual elements. We talked about single, double, and triple bonds. Keep in mind, hydrogen is our first exception to the octet rule in that it does not need 8 electrons around it. It is happy with 2. It will form one single bond. Now, before we get into drawing more interesting Lewis structures, we are going to talk about electronegativity and polarity. So electronegativity is the attraction of an atom for the shared electrons in a covalent bond. So even though two atoms are sharing electrons, they're not always sharing equally. Think about kind of a tug-of-war situation. The electronegativity scale shows increasing electronegativity going up and to the right on the periodic table. Noble gases are not included. What you can always remember is fluorine is the most electronegative, and the closer to fluorine you get, the more electronegative the element. So when we have bonds between atoms of different electronegativities, those 2 electrons in the bond are not being shared equally. We get a dipole. We get a pull of electrons towards the more electronegative element, creating partial charges, a positive on the carbon, a negative on the fluorine. This little symbol here is a little delta. It means partial charge. So it's not a full plus or minus, but you have more negative charge on this side of the bond, meaning it's more positive on this side. When we talk about bonds, so far we've said ionic or covalent, but we're going to look at that in a little more detail here. Polar covalent versus non-polar covalent. So if those electronegativities are big enough, when you see, say, a metal on the left side of the table versus a non-metal on the right, you get an ionic bond. When you have a moderate difference, you get a polar covalent bond where they're sharing the electrons. They're not forming ions, but it is an uneven sharing. If you have 2 atoms that have similar to the same electronegativities, say you have something like a carbon-carbon bond, this would be non-polar covalent because neither carbon is going to be pulling harder on the electrons. So when we go to answer this question here, which bond is most polar, the CH, the OH, or the HCl, well, hydrogen and chlorine are farthest apart on the periodic table, meaning they're going to have the biggest difference in electronegativity. Chlorine is going to be pulling those electrons in that single bond much harder than the hydrogen. All right, so that would be the most polar. All right, so now that we have thought a little bit more about the covalent bond, let's look at Lewis structures and bonding. Strategy for drawing Lewis structures. It's always good to go in with a strategy. There is a 6-step process here. You may need 3 to 6 of the steps depending on the compound that you're drawing. We're going to start simple, and we're going to look at methane. We're going to start with CH4. Now, in the first step, you need to always count your valence electrons. Carbon has 4 valence electrons. Hydrogen has 1. We have 1 carbon and 4 hydrogens, so we have 8 valence electrons. It's important that your Lewis structure always has the correct number of valence electrons. Now, step 2, we're going to draw the skeletal structure. So we're going to place our atoms. Now, typically, in the formula, the first element that's listed is the central atom. Except when that's hydrogen. Hydrogen can't typically be in the center because it only forms 1 bond. So we're going to place our atoms. We're going to put carbon in the middle with our little hydrogen surrounding it. Step 3, we need to add single bonds to connect all atoms to the central atom. Otherwise, they're just floating in space and it's not part of the molecule. So here we add 1, 2, 3, 4 single bonds to connect our atoms to the central atom. Now, step 4 here is really important. It's where we check our octet rule. We place remaining valence electrons to satisfy octets. Now, I need to do a little inventory. I've used 2 electrons for each single bond, so I've used 2, 4, 6, 8 electrons. I don't have any more electrons. Is the octet rule satisfied? Carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. It's happy. Hydrogens each have 2. It's an exception. The hydrogens are all happy. This is the complete Lewis structure for methane. There are no more valence electrons. All of the rules are satisfied. If you have enough, if you have more electrons, we will deal with that in one of our practice problems. We will see what to do if we don't have enough electrons using step 5, and we will see what to do if we have too many electrons in step 6. We will see all of those being used in our practice problems. So let's get started on some practice problems. I've already gone ahead and filled in the number of valence electrons. Okay, so let's start with ammonium trichloride. All right, you've got 5 valence electrons, 3 chlorines with 7 each, so we have 26 valence electrons. Nitrogen's listed first, so we'll put it in the middle, and we'll pop our chlorines around it. We need to connect them with single bonds. Now that's going to be, let's see, 2, 4, 6 electrons. We still have 20 more to go. We're going to place them to fulfill octets, and I would always start with the outer atoms. Use that center atom last. That'll help you later on. So this chlorine only has 2. It needs 6 more. So I've got 6 electrons added here. I've got 6 I need to add to this chlorine and 6 to this. Now check in with your inventory. I have, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Bear with me while I try to count. Here we go. I have 2 more left. I have 26 total. The nitrogen only has 6 around it. So this one wraps up really nicely with that final pair on the nitrogen. Now, everybody has a full octet. Every atom has access to 8 electrons. We have used all 26 of our electrons. This is a good Lewis structure. All right. Here we go. Let's look at CO2. We have 16 valence electrons. Put carbon in the middle, oxygen on the outsides, connect to the central atom. We still have 12 more electrons. Now, if I start with my oxygen here, I've got 2, 4, 6, 8, 10, 12, 14, 16. Now I've used all of my valence electrons. The oxygens are both happy, but the carbon is not. The carbon only has 4 valence electrons. I don't have any more. I can't just create electrons. So what I'm going to do is I'm going to take lone pairs from the oxygen and I'm going to share. I'm going to share the lone pairs from an oxygen on either side. So I'm going to go ahead and I'm going to erase that pair, and I'm going to erase that pair, and I'm going to create double bonds. All right, now take a look. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, and 8. Oxygen, 2, 4, 6, and 8. Everyone is happy. Total, we have 2, 4, 6, 8, 10, 12, 14, and 16. When you don't have enough valence electrons to get to an octet with lone pairs, then you share. This is when you're going to know to make multiple bonds. All right, moving on. If we look at CF2Cl2, we have 32 valence electrons. We're going to put carbon in the middle. It really doesn't matter if the fluorines and the chlorines are on the top, bottom, left, or right. Just put them around. We're going to connect with single bonds. So I've used 8 of my electrons. I know carbon's happy now, 2, 4, 6, 8, but each of my halogens on the outside only have 2. So they each need 6 more. So I'm going to count down. I've got 8 already. Let's put in 9 and 10, 11 and 12, 13 and 14, 15 and 16, 17 and 18, 19 and 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. This worked out great. Everybody has a complete octet. All 32 electrons have been used. This is complete. All right, what to do with ions? It's going to affect your total electron count. All right, I have 5 electrons from the phosphorus. I've got 4 oxygens with 6 electrons each. And I have to add in an additional 3 because it's a -3 charge. So let's do some math because I wasn't preparing. I've got 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so we have 32 electrons again. We're going to pop that phosphorus in the middle, oxygens all around the outside, 2, 4, 6, and 8. Very similar to the last problem, we want to complete those octets on the oxygens. So we're going to have 10, 12, 14, 16, 18, and 20, 22, 24, 26, 28, 30, and 32. Again, complete octets. Everybody's happy. For our let's see, our chlorite ion here, we have 7 from the chlorine, 6 from each oxygen, and an additional 1 because it's a negative charge. So this is going to be 12. So we have 20 valence electrons. So chlorine's going to go in the middle because it's listed first. Put the oxygens on the outside, 2, 4. We're going to complete our octets, starting with our outer atoms. So we have 4, 6, 8, 10, 12, 14, 16. Now we don't share because we still have some more. I've only used 16, but I have 20 total. I have 4 more, and 18, 19, and 20, 17, 18, 19, and 20 can go on that chlorine. There's no reason to make a double bond. Don't make multiple bonds unless you need to. So we've used all our valence electrons. We have a valid Lewis structure. Now let's do a cation before we move on to our exceptions. We've got an ammonium ion. It's got 5 from the nitrogen, 4 from each 1 from each hydrogen, and we have to subtract 1 because this is a positive charge. We have 1 less electron. So we're going to put the nitrogen in the middle, pop in our hydrogens, 2, 4, 6, and 8. Well, we've seen something similar to this. We have a complete octet around that nitrogen. We've used all 8 all 8 electrons. Hydrogen's happy with just a single bond and 2 electrons. That's a valid Lewis structure. Now, before we think about what can be done if we have too many electrons, let's revisit this idea of exceptions. We already know that hydrogen can have less. Hydrogen only needs 2 electrons to be happy, so you get 1 covalent bond. Beryllium is happy with 4, so it tends to form 2 bonds. And boron is happy with 6, so it tends to form 3 bonds. These are beryllium and boron are less likely to show up for you. Hydrogen we see all the time, that's why we started with it. Now, you will frequently see exceptions to the octet rule where you have atoms that can have more than an octet. In this case, or elements that allow that are in period 3 and below. Essentially, the atom has to be big enough to take those extra electrons. So we have a couple of examples here. We got our old friend sulfur hexafluoride. It's going to have 48 electrons total. We're going to follow all the same rules. Sulfur, surrounded by our 6 fluorines. We have 2, 4, 6, 8, 10, and 12 electrons connecting all of our fluorines to our central atom. And now we're going to use valence electrons to complete our octet. So what did I say? We have 12 already, 14, 16, 18, 20, 22, 24, 26, 28, and 30. 32, 34, 36, 38, 40, 42, 44, 46, 48. Whew, I'm always relieved when I count correctly. All the fluorines have a full octet, but notice sulfur has more than an octet. Sulfur's in period 3, so that's A-OK. This is a valid Lewis structure. Next, we're going to move over here to xenon. Xenon tetrafluoride. Here we go. Follow the same rules. We have 36 valence electrons. So xenon has, sorry I switched colors. There's no reason for that. Xenon has 4 fluorines surrounding it. 2, 4, 6, and 8. We're going to go ahead and complete our octets of our fluorine. 10, 12, 14, 16, 18, and 20, 22, 24, 26, 28, 30, and 32. Now I've used 32 electrons, but I have 36. Everybody has a full octet. The fluorines all have 8, xenon has 8. Go back up here to step 6. Take a look at this. If you have filled your octets and have extra electrons, place extra on the central atom in lone pairs. So we have 4 extra electrons. We are going to place them in lone pairs, so 34 and 36. Place them on that central atom and do your best to make it not look like it belongs to one of the fluorines. Now, everybody has a full octet. The extra electrons are placed on the central atom. That is a valid Lewis structure. The last topic I want to cover in this video is resonance. Sometimes more than one valid Lewis structure is possible. Let's consider sulfur dioxide. Now, sulfur dioxide has 18 valence electrons. Sulfur in the middle, oxygen on the outside, 2, 4 of our electrons to connect. We're going to complete octets. So we have 2, 4, 6, 8, and 10, 12, 14, and 16. We have 2 more and sulfur is lacking, so 17 and 18 go on sulfur. Now this is not a complete Lewis structure because our sulfur is lacking a full octet. Now when I don't have enough, remember I want to share so that I can complete the octets. So I'm going to go ahead and I'm going to erase that lone pair and I'm going to draw in a multiple bond. Now this oxygen has 2, 4, 6, and 8. Sulfur has 2, 4, 6, and 8. And this oxygen has also got a complete octet. There is no reason, though, that I had to share from this oxygen and not this oxygen. So there is another valid Lewis structure where I shared electrons with the oxygen over there on the right, and the oxygen on the left still had 3 lone pairs. Both of these are valid Lewis structures, and both of them are important. We say these are resonance structures, and we use a resonance arrow. What this tells us is that neither one of these Lewis structures alone is enough. Sulfur dioxide winds up not having a single bond and a double bond. When you actually look at the structure, both bonds are the same length. Usually a double bond is shorter, a single bond is longer. In this case, the sulfur dioxide has 2 bonds that are equal in length. So in reality, the structure is a hybrid. Sort of how a mule is not a horse on Monday and a donkey on Tuesday. It's always a mule. It's a little bit of both. Sulfur dioxide is never the left-hand structure and then switch to the right-hand structure. It's always a hybrid of the two. Benzene is a good example of this as well. It's a pretty important chemical structure. It's a 6-membered ring of carbons with alternating double bonds. However, there's no reason that I drew those alternating double bonds the way that I did. This is the resonance structure of benzene. So all of the atoms are connected in the same way. The only difference is the placement of the electrons in the Lewis structure. This gives us a lot of information kind of about the stability of benzene. I think for now, let's end this video here. We'll come back to bond theory in another video. Thank you.